general relativity, step by step. I've been considering this particular line element minus f of r dt squared plus, no, that's a g of r dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. So there it is, and I'm going to write it out in a matrix format as well because it'll be nice to refer to later on. 0, 0, 0, 0 g of r, 0, 0 for that g is this g here, 0, 0 r squared, 0, 0, 0 r squared sine squared theta. Now what I want to do is to work out the, well, ultimately work out the Ricci tensor. Well, ultimately I'd like to work out the whole of the Riemann-Christoffel tensor, but we'll start with the Ricci tensor. And to do that I need to work out the Christoffel symbols. Christoffel symbols. So what I'm going to do is just work out a few of these just to show you how it works. So I'm going to choose this one. This is just an example. T, T, R. So I'm just going to work out what that is. So that tells me that alpha equals T because it's the top one, beta equals T because it's this index here, and gamma equals R. There we go. Now, alpha equals T. Let me just write out the definition of the Christoffel symbol. Let me write it out here. Here. Alpha, beta, gamma equals a half G alpha delta, and we're going to contract over delta, di G blah blah di X blah plus di G dd by di X dar minus di G, just a minute, di G dd by di X do. Right, and the delta sums the first place, the second place, the bottom place. We've got beta and gamma to assign, beta and gamma, beta down there, gamma in there, and beta and gamma that way. Okay, and it's summed over delta, of course. So what this tells me is that we're going to sum across this delta, but I don't need to worry about any value of delta apart from delta equals t. Why? Because the metric tensor itself is diagonal. Actually, yeah, that's g with the lowercase. But of course, because it's diagonal, ij, it's still, the matrix inverse is still a diagonal matrix. So that tells me that delta equals t because it's the only non-zero component on its row. One column. Okay, so that equals t, tr. Let me get this right. It's a half g alpha equals t, delta equals t, times di g delta, which is t, beta from here is t as well, by di x gamma, gamma is r, plus di g gamma equals r, delta equals t from here, by di beta t, minus di g beta equals t, beta equals t, gamma is the next one, which is r, by di x delta, and we know that that's t. Well, that's great. I'm going to switch to red and do a bit of cancelling here. No, I'm not. Just a minute. Oh, well, I don't appear to be able to change to red. Never mind. This term is identically 0 for two reasons. First of all, because we're considering an off-diagonal element of the metric tensor. It's this one here, I think, which is 0, constant. And secondly, because we're differentiating with respect to time. And I set up the original element here so that there was no time dependence in any of the entries. Likewise, this one's 0 for the same reason. So we are left with a half g superscript tt di g lower subscript tt by di r equals a half we invert this matrix here, so when we invert a diagonal matrix, we just invert the diagonal elements, and so it's going to be minus 1 over f of r times di by di r of dtt, which is just f of r. And we can write that out a slightly more easily, slightly more compact notion, minus f over, f dash, I'm sorry, over 2f. And that is the first, not the first one, but just this random example, which I chose carefully to be non-zero. However, you can see that there's quite a lot of work here, because there are potentially at least 4 times 4 times 4 equals 64 terms. I guess we know that they're symmetrical in the lower terms. So we've got potentially 32 of these things to work out. And this one's a relatively straightforward one. When you start fooling around with sines and d-phi's and r-squareds, it suddenly gets a lot harder. It's not hard. It's just involved algebra, which is very easy to make a mistake. But fundamentally, it is an algorithmic process. All you need to do is to keep your wits about you and write down all these other terms. And so we could, in principle, calculate any other term. We could put theta, phi, t if we wanted. I don't know what that is offhand, but we could work it out using the same method. Well, that's not terribly edifying. So what I'm going to do in the next screencast, I'm going to stop here. In the next screencast, I'm going to use symbolic computational software to evaluate these things, to save me the bother, basically, because it's not very edifying or informative or instructive to derive all of them by hand. So I'm just going to use software. Stop there. Stop, 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 stop.